Well, hello, welcome to the 2.2 lesson video on Introduction to Functions. Okay, so functions. What is a function? Well, a function means everything you put into it can only have one thing that you get out. So what does that mean? You put in something, you get out something, and it can never be different. So if you put in 5, you always will get 7. But if you put in 5 and then you get out a 7 and a 9, that is a problem. Well, let's see this in action. Exercise 1, it says consider the function rule, multiply the input by 2, and then subtract 1 to get the output. Okay. So we are going to multiply the input by 2, then subtract 1. Let's fill in this table. We're going to multiply the input by 2. So we'll multiply 0 times 2 and then subtract 1. So 2 times 0 is 0, subtract 1 leaves us with -1. And definitely use your calculator for this if you're having trouble with the integer rules. All right, 2 times 1. So we're going to multiply the input of 1 by the 2 that they said, and then deduct 1. So 2 times 1 is 2, take away 1 is 1. Let's do the same thing. We'll multiply 2 by 2, then subtract 1. 4 minus 1 is 3. And lastly, we are going to multiply the input of 3 by 2, which is 6, minus 1 is 5. Now down below, it's asking us to write the equation that gives this rule in symbolic form. So let's just use x's and y's since our input is x and our output is y. So how did we get y? Well, we took 2 and we multiplied that by x, so 2x, take away 1, subtract 1, and that gave us our output. Hey, that looks like y equals mx plus b. Pretty cool. All right, let's graph this function rule on the graph. So it looks like when our x is 0, our y is -1. When our x is 1, our y is 1. When our x is 2, our y is 3. So 2 to the right, 3 up. And then when our input is 3, so 3 to the right, our output is 5. 5 up. And as you can see, this is making a linear relationship. So we have a line with a slope of 2 and a y-intercept at -1. Exercise 2 asks a very interesting question. So it talks about the function rule for number 1, what input would be needed, so what input is needed to get this output of 17. Well, we don't know the input, so we're going to just leave that in x, but they did tell us the output is 17. What could we do with this? Well, let's solve it. I'm going to sort. So I'll get 2x is equal to 17 plus 1. Oh, I'm running out of space, but 2x is equal to 18. And if we divide both sides by 2, we would get x. I'm just going to write this up here. I need to write smaller. X is equal to 9. And then it asks, why is it hard to find an input when you have an output than finding an output when you have an input? Well, I guess it looks like we probably have to do some solving of an equation when we're given the output. Because if we just had an input, which is everything that we did up above, it was really easy. You just substituted and simplified. Here, we had to use that equal sign, so we actually had to bring in an equation. So just to summarize, if we had an input of 9, that would produce an output of 17. All right, moving on to exercise 3. A function rule takes an input n, I usually like to see x, but whatever, and then it converts it into an output y. And it does this by increasing half of the input by 10. Half of the input, so half of n, and then it increases it by 10. All right, so half of the input increased by 10. All right, and what will we do when we get this? Well, that will produce our output of y. Reading on, it says determine the output for this rule when the input is 50, and then write an equation for the rule. Hey, looks like we already wrote the equation. Part of this is done. Let's now, I'm going to do this in a different color. We're going to find the output, so we need to find the y when we input 50. Okay, so half of 50 is 25, and we're going to add 10 to that to get our y. So half of 50 is 25, and of course we still need to add the 10, so 25 plus 10 is 35. So our output of 35 is what we get when we input 50. In, out. All right, exercise 4 is pretty interesting. We don't see any numbers. We see children and the month that they were born. So functions actually don't have to be numerical. They just have to input something, and every time you put in something, they have to get an output that is unique to that input. So for example, Max. It's not possible for Max to be born in both January and February, because if that were the case, this would not be a function. But it's a function because Max is born in January. Evan is born in April. Zeke is born in May, Rosie is born in February, and Nico is born in May. And some of you might say, wait a minute, Zeke and Nico, they're breaking the rules. But wait a minute. A rule for a function is what you put in can only have that one out. So it doesn't matter that Zeke and Nico were both born in May. It would be a problem if Zeke was born in both May and February, which we know is impossible. So why is this rule a function? Well, every input has its own output, has only one output. All right, what is the output when the input is Rosie? All right, so let's look. You put in Rosie, she was born in February. So we put in Rosie, we got out February. So the output is February. And reading question C, it says find all inputs that give an output of May. Well, we've already talked about this, Zeke and Nico. And why does this not violate the definition of a function? Well, it really doesn't matter that the outputs repeat. It's when the inputs repeat that's a problem. So just to summarize why this doesn't violate the definition of a function, because Zeke and Nico each have their own unique output. And I don't know why this autocorrect keeps changing Zeke to Z-E-E-K. Let me see if I can fix this. Ah, much better. Sorry, Zeke. All right, let's move on to exercise number 5. Charlene, she's heading out to school by foot on a fine spring day, and her distance from school is in blocks, is given as a function of the time in minutes. So it looks like she's walking, the number of minutes that go by, and that is going to help us to determine the distance from school in blocks. So A, how far does Charlene start off from school? So starting off, this is a very important concept to talk about. This is what we call the initial value. So when she hasn't spent any time walking, so when her time is 0, she has traveled, well, let's be careful of the scale here. So 2, 4, 6, 8, 10. Ooh, looks like we're counting by twos. 12, 14, 16, 18, 20, 22 blocks. Okay, part B. What is her distance from school after she has been walking for 4 minutes? So 0, 1, 2, 3, 4 gives us this output right here, which happens to happen at 14 blocks. Okay, C says after walking for 6 minutes, which is right here, Charlene stops to look for her subway pass. Oh, that kind of makes sense. Look at her distance does not change between these two blue sections. So how long did she stop for? Well, that was from 6 to 7 to 8 to 9 minutes, which is a total of 3 minutes. Sorry, we have 2 more sections. D. Charlene then walks to a subway station before heading to school on the subway. How many blocks did she walk to the subway? Well, that's interesting. It looks like she had to go a little bit farther to get closer because it looks like the subway took her there a lot faster than she would get there by foot because the slope is a little bit steeper from here to there. So it looks like here is where she's walking to the subway. So how many blocks did she walk to the subway? Well, we started from 10, then went up to 20. So we started at 10 and then went up to not 20 to 12. So that would just be 2 blocks. And lastly, how long did it take for her to get to school once she got on the train? Well, here's where she picked up the train, and we can see that she is 0 blocks from school when we hit 15. So that would be between 11 and 15, which is a total of 4 minutes. Okay, folks, that wraps up our 2.2 lesson.